Hello, and welcome back to Introduction to Genetics and Evolution. In the previous videos, we've talked about deviations from the Hardy-Weinberg equilibrium. The most recent videos, we talked about natural selection. This is very predictable changes in response to differences in fitness. Now, one of the assumptions of Hardy-Weinberg that I mentioned before was an infinite or near infinite population size. Obviously, there are no species out there that have an infinite number of individuals. As a result, there will be some sampling error, or as this is referred to here, genetic drift. In this video, we'll talk about the effects of sampling error over single generation. Now, contrasting natural selection with genetic drift, natural selection is highly predictable. You have a subset of genotypes that have higher fitness than other genotypes. This higher fitness is associated with having more offspring, and as a result, these genotypes become overrepresented. Now, if you know the fitnesses associated with the different genotypes, then the changes in allele frequency associated with natural selection are very highly predictable. But not all evolutionary change is this predictable. As I mentioned, species typically have finite numbers of individuals. As a result of that, random chance matters. Let me start with an analogy. Let's look at a bag of marbles. Let's imagine that you have brown marbles and blue marbles only in this bag, and exactly half the marbles in the bag are brown, exactly half the marbles in the bag are blue. Now what's going to happen is you're going to start a new bag of marbles. Now what if we start this new bag of marbles with exactly 4 marbles from the old bag, and we just reach in and randomly pick out 4? How many of each color would you get? Well, you could get 4 blue, you could get 4 brown, you could get 2 blue and 2 brown. Now, probabilistically, there's only about a 5% chance that you get all 4 marbles the same color. You'd either get 4 blue marbles or 4 brown marbles. Not very likely. So you're going to have a mix of colors in the new bag that you start. So this is associated with having 4 marbles starting the new bag. Now what if you started the bag with even fewer? What if we started with exactly 2 marbles? Well, how many of each color would we get? Well, there's 3 possibilities. 2 blue, 2 brown, or 1 blue and 1 brown. And in fact, in this case, there's about a 50% chance that the 2 marbles we'd get would be the same color, that we'd either get 2 blue marbles or 2 brown marbles. Well, this illustrates the point of sampling error. So this prior example, when you picked 4 marbles, it's likely you'd get roughly the same proportions as you had in the previous bag, right? So this would be the right proportions, that it mimics the previous generation. If you pick 2, you're very unlikely to get even roughly the right proportions. So by picking more, you tend to get a more representative sample of the original pool. This is the principle that we see in general. If you want to understand if people in a particular supermarket are tall, you don't just look for one person, but you look for a lot of people. So you get a representative sample. Well, the same principle applies in nature. Again, populations are not infinite, and frequently small samples are not perfectly representative, and these are the ones that form the next generation. Because they're not perfectly representative of the previous generation, the allele and genotype frequencies change between these generations. And this effect can compound more and more over time. We'll talk about the compounding effect over many generations later, but let's focus instead on what's happening in one generation. So it's random in direction over one generation, whether you're going to increase in frequency or decrease in frequency. So assuming that there is more than one allele, so assuming you have at least 2 alleles, any allele is about equally likely to increase or decrease in frequency after one generation of sampling error or genetic drift. So for example, if the allele frequency of big A, assuming there's 2 alleles, big A and little a, if the allele frequency of big A is 0.6, you're about equally likely to have frequency above 0.6 or below 0.6 in the next generation. However, it's very unlikely you're going to have exactly 0.6 again, because there is a decent chance you're going to have some non-representation. Even if you're having a very large sample, it might end up being 0.603 or something like that. So allele frequencies tend to drift due to this sampling error, and this is where the term genetic drift came from. Let me show you what would happen in the context of this. Imagine tossing a coin 10 times. So this is similar to having p equals 0.5. You may get 5 heads from these tosses, right? So that would be exactly what's expected in the sense of the average, right? Since you're equally likely to get heads or tails. Now getting more than 5 heads or getting fewer than 5 heads is equally likely. This shows you the distribution that you expect, the probabilities. Probability of getting exactly 5 heads is actually less than a quarter. Your probability of having 10 heads is extremely low. Probability of having 0 heads is extremely low, but you're about equally likely to have slightly more or slightly less than 5 heads when you toss the coin. Okay? In fact, actually, the probability of getting 10 heads is about 1 in 1,000. It's very unlikely, unless it's a weighted coin. Well, the same concept applies to populations. So if your original population has an allele frequency of big A of 0.6, you see below what would happen in one generation of genetic drift. The probability of having it greater than 0.6 versus less than 0.6 is about the same. And this is the case if you have 10 diploid offspring. Okay? Now, let's see what happens as we look at this over multiple generations briefly by just looking at the individual steps. So this magnitude of change compounds as it relates to population size. Now, greater changes are going to occur if the population size is smaller. You will have greater individual deviations in allele frequency per generation as the population is smaller. So let's look at 3 different population sizes. Let's look at population size 400. You're starting, in this case, this is looking at generations on the x-axis and allele frequency on the y-axis. You're starting at 0.5. And what's happened here is we're starting 1, 2, 3, 4, 5, 6, 7, about 8 different populations at 0.5. And this shows random changes over all 8 populations. After about 100 generations, we see there's a few that are kind of close to 0.5. Some of them are higher, some of them are lower. So we have this genetic drift that's compounded over time. This shows, this little green figure, shows the approximate average size of a change in one generation in any of these populations. Now let's see what happens if we reduce this. Instead of 400, what if we looked at a population of size 40? Well, we see in this case much bigger changes. We have some alleles that have gone all the way to 100% or 0% in some of these populations, and some are still segregating. But again, you're equally likely to go up or down in any individual generation, and the individual step size now is much bigger. You get bigger random changes in allele frequency with smaller population sizes. Right? Let's do the same thing. This was with population size of 40. Let's look at it in the extreme with population size 4. Wow, all variation is lost. We'll come back to this actually very shortly. But you see, the individual step sizes here is very large. Again, in each of these cases, these are 8 different simulations, each with population size 4 and starting the allele frequency at 0.5. Now, how big are these steps on average? Well, again, the average change in allele frequency due to one generation of drift can be approximated with this. It would be PQ divided by 2N, where P and Q are the allele frequency, say for big A and little a, and N is the population size. Okay? So just to look at this in terms of the numbers we were just looking at, if N equals 4 and P and Q is 0.5, the average change is 0.03. Now again, this is the average change per generation. Some individuals will change by 0.03, some will change by more than 0.03, some will change by less than 0.03. And then again, some are going up in frequency. So in this case, big A is becoming more abundant. Some are going down in frequency. In this case, big A is becoming less abundant. So this is what's happening when N is 4. When N is 40, you have a much smaller average change. And when N is 400, you have an even smaller average change. And you can see from this last one, given this very small average change, that's why even after 100 generations, all the populations were still variable in the ones we looked at. Now, obviously, if you went much longer than that, that wouldn't still be true. But in 100 generations, you still had variation when population size was 400. In contrast, you lost all variation when the population size was 4. We'll come back to that in just a moment. But again, I just wanted to emphasize this average change is related to both the allele frequencies and related to the population size, where bigger populations have smaller average changes in allele frequency due to drift. So here are the take-home messages from this video. Drift is strongest in small populations. Drift is neither predictable in direction nor exactly replicable in degree in one generation. That you saw with all those different populations, even when we started it over and did it again, they didn't all follow the exact same track. They all had the same, on average, change in allele frequency, but since some went up, some went down, some had a little bit more than average, some had a little bit less than average at times, it's not exactly replicable in degree, and it's not predictable in direction in one generation. Very important addendum there. And finally, drift can cause big changes in allele frequency over time. We'll pick up on this in the next video. Thank you.